For years, the deadliest mystery in the auto industry had no answer. Brand new trucks were seizing on the highway. V8 engines locking solid with barely 1,000 miles on them, and every automaker pointed at something different. Every one of them was wrong. Then engineers at rival companies, each hunting the same killer inside their own engines, finally cornered it at the same time. And the thing tearing apart $80,000 SUVs and near-new pickups was not a flaw in the design, a software glitch, or a bad tank of fuel. It was a single fleck of metal small enough to vanish in the palm of a hand. This is what they found. Roadside nightmare. It starts as a faint metallic tap somewhere under the hood. A driver on Interstate 95, a loaded trailer riding behind a Silverado, financed 90 days ago, turns the radio up and keeps moving. A mile later, the tap is a knock, then a hammer. Then the whole truck shudders and the engine locks solid. The power steering dies. The brake pedal turns hard as stone underfoot. The hazard lights blink while traffic stacks up behind him. He wrestles 2 tons of dead metal onto the shoulder, kills the ignition, and sits with his hands on the wheel as semis blow past close enough to rock the cab, waiting on a tow for a near-new truck with a payment book thicker than the owner's manual. That scene was not the rare one. By late 2023, it was the common one. Owners of 2021 through 2024 Silverados, Sierras, Tahoes, Yukons, Suburbans, and Escalade were describing the same pattern. A faint bearing knock, a tick on cold starts, a whiff of burnt oil, then total seizure within days. Many of the trucks had under 30,000 miles. Some had less than 5,000. People had financed them new, some paying over $80,000 for an Escalade, changed the oil on schedule, and followed the manual to the letter. The engine died anyway. What unsettled the mechanics most was how little warning the failure gave. A worn part usually announces itself for weeks with a rough idle or a check engine light that nags an owner into the shop. This was different. The first symptom was often a tick faint enough to blame on a loose heat shield. And by the time it grew into something impossible to ignore, the engine was frequently hours from seizing rather than days. Drivers who heard it on a Monday and planned to book the truck in over the coming weekend sometimes never got the chance. In April of 2025, General Motors made it official. The company recalled 597,571 vehicles in the United States, part of a worldwide action covering more than 700,000. The National Highway Traffic Safety Administration, or NHTSA, traced the problem to manufacturing defects in the engine's connecting rods and crankshaft, defects that could let the V8 fail without warning across certain Cadillac, Chevrolet, and GMC models. By the time GM acted, its filings counted more than 14,000 reports from owners whose engines had lost power, 14,332 in all. Overnight, the L87 6.2-liter V8, one of the most popular engines GM had ever built, became the most talked-about engine in America for the wrong reasons. The recall did not arrive in a single stroke. The affected fleet was split across more than one service bulletin, and the build window that mattered ran from early 2021 into the spring of 2024. Owners began receiving notification letters in the middle of 2025, many of them carrying interim guidance. Listen for a knocking noise from the engine and treat any sudden loss of power as a reason to pull over safely, because the failure could strip away propulsion without warning. For a stretch, the most practical instruction the automaker could offer some owners was to stay alert to a sound. At the dealerships, the service network buckled. Phones rang off the hook. Loaner cars were gone by mid-morning, and tow trucks dragged in dead V8s faster than technicians could tear them down. A full engine replacement on one of these trucks runs well past a dozen hours of teardown, the better part of 2 working days per vehicle. Stack dozens of those jobs on a single shop with a handful of trained technicians and a few lifts on top of the ordinary oil changes and brake work that keep the lights on and the whole system clogged. Owners were quoted wait times measured in weeks and months, not days. The bottleneck was never parts on a shelf. It was raw shop hours multiplied across a recall this size, hitting a network with no spare capacity to begin with. The scale drew lawyers as well. Class action complaints followed, alleging GM had sold vehicles it knew or should have known could fail. And between replacement engines, dealer labor, loaner fleets, and litigation. A recall this large carries a cost heavy enough to register on a balance sheet, all before the question of whether the fix even worked had been settled. Then came the part that turned a bad recall into something stranger. Even after the official remedy rolled out, the failures did not stop. NHTSA logged at least 36 complaints from owners whose engines had already received the fix and failed anyway. Some of those owners had been handed brand new replacement engines under warranty. Those failed too. So, in January of 2026, NHTSA opened a fresh recall query with a single question behind it, whether the fix was a fix at all. And the official recall may not even mark the full boundary of the problem. Regulators have logged well over 1,000 reports of bearing failures tied to this V8, including some in trucks and SUVs built outside the recall window, entirely from model years the campaign never touched. That is why the query kept widening instead of quietly closing. The agency had already signaled that the boundary might be wrong. Before the post-repair complaints forced the question of the fix itself, NHTSA had opened a separate engineering analysis to test whether engines built outside the recall window were failing the same way, including some from the 2019 and 2020 model years that the campaign had never covered. Taken together, the two actions describe an investigation chasing a moving target, not only whether the remedy works, but whether the recall ever drew its lines in the right place. The reason the same failure keeps surfacing has little to do with one bad factory and everything to do with how a modern engine is built. To see it, the trail has to go inside the engine itself. A modern engine is a different world from the V8S of a generation ago. The bearings ride on a film of oil thinner than a human hair. The clearances, the gaps between moving steel parts, are measured in microns, and a micron is 1,000th of a millimeter. The connecting rods are forged so precisely that a fingerprint left during assembly can throw a measurement off. Even the oil changed. Most of these engines were filled with 0W20, thin enough to pour almost like water next to the syrup poured into engines decades ago. A single human hair runs about 70 microns across, and the film of oil holding a spinning crankshaft off its bearing can be a small fraction of that. The gaps are so tight that temperature alone matters. A part measured on a cold morning is not quite the same size as the same part measured on a warm afternoon because the metal expands and contracts. These are not loose, rugged machines that tolerate a little slop. They're instruments built to tolerances a mechanic in 1985 would have called impossible. The assembly runs to the same standard. Bearings are graded and matched to journals by size class, so the clearance lands within microns of target. The torque on the rod bolts is controlled to a measured degree of stretch rather than a rough feel, and parts are held at a controlled temperature because a few degrees changes their measured size. An engine like this is less assembled than calibrated. And a calibration that exact has almost no room for a contaminant that was never in the specification. The reason they're built so tight and so thin comes down to economy. Federal rules keep pushing automakers to wring more miles from every gallon. Thin oil cuts friction. Tight clearances cut waste. Small turbocharged engines do the work the big lazy V8S used to do, squeezing the power of 8 cylinders out of 6 or even 4. On paper, it is brilliant. More power, better mileage, fewer emissions, all at once. Turbocharging raises the stakes further. A small boosted engine making the power of a larger one has to survive far higher cylinder pressures and temperatures, forcing more heat and more load through bearings that are already smaller and more tightly fitted than the ones they replaced. The same downsizing that earns the fuel economy number also pushes every internal part closer to its limit. A bearing in a big, naturally aspirated V8 lived an easy life. The same bearing in a boosted, downsized engine works harder for every mile it turns. Build an engine this tight, and anything left behind during manufacturing becomes a weapon. A metal shaving, which the industry calls swarf, that would have washed harmlessly through a 1995 small block now wedges into a modern bearing and tears the engine apart in seconds. It jams into a gap narrower than a hair and turns a spinning crankshaft into a grinding wheel. That is the irony buried in the design. The same impossibly tight build that makes a modern engine efficient is what makes it fragile. The old engines were crude, and crude turn out to be forgiving. The new ones are precise, and precise turn out to be unforgiving the moment a single speck ends up where it does not belong. Industry analyses commonly attribute a large share of mechanical engine wear to particulate contamination rather than to design flaws, abuse, or heat. By that logic, most engines that die young are not wearing out. They're being ground down from the inside by dirt, debris, or microscopic metal that should never have been in them, circulating in the oil from the first second they run. The obvious question is why the oil filter does not simply catch the debris. And the answer is a matter of timing and geometry. Much of the damage is done on the very first run before the oil has made enough passes through the filter to scrub itself clean. And the most dangerous particles are the ones already lodged in the oil galleries downstream of the pump, fed straight into the bearings before any filter sees them. A filter also carries a bypass valve that opens when the oil is cold or flow is high, routing unfiltered oil through to guard against starvation. And a cold start is exactly when a fresh engine is most vulnerable. The filter is a safety net strung in the wrong place to stop this particular fall. Picture a doorway. An old engine bearing was a wide doorway with room to spare, and a person could walk through it wearing a backpack and nobody would notice. A modern bearing is a doorway built to the exact width of a person's shoulders with no clearance at all. Try that one with the same backpack and the frame jams and the wall tears off its hinges. The backpack is the debris. The doorway is the clearance. The modern engine has spent 2 decades narrowing every doorway it has. Here is where these engines actually die. The crankshaft never touches the metal around it. It floats on a microscopic wedge of pressurized oil, a film measured in fractions of a hair. And that film is the only thing keeping 2 pieces of hardened steel from grinding together thousands of times a minute. Force a hard particle into that film, and the wedge collapses. Metal kisses metal. The bearing scores, then galls, then welds itself to the journal, and the rod riding on it tears free from the cap. That is a knock, then a hammer, then silence. Inside, it is a small explosion the engine never walks away from. The reason a single speck matters so much comes down to how the bearing is lubricated. In normal, running the crank and the bearing are held fully apart by that pressurized film. Estate engineers call hydrodynamic lubrication. And while it holds, almost nothing wears at all. But the film has a thickness. And once a particle harder and larger than that film enters the gap, the 2 surfaces are forced into contact for an instant, scratching the soft bearing and the hardened journal alike. Each scratch disturbs the film a little more, and the damage compounds until the film can no longer form and the bearing is left running dry against steel. Back to the factory, the debris has to come from somewhere, and the trail leads off the road and onto the factory floor. Crankshafts and connecting rods begin as forged steel and are carved into shape by machining. And machining throws off tiny metal shavings by its nature. Every cut, every drilled passage, every smooth surface sheds a little debris. The plant's job is to blow it out, wash it off, and inspect every passage before assembly. And in a perfect plant, it is all gone before the engine is bolted together. But push production into the millions of units a year with lines moving fast enough to hit those numbers, and perfect is not on the menu. Some oil passages get missed. Some shavings cling to a surface under a film of oil residue, invisible to a quick look, waiting for the engine's first heartbeat. Multiply a small miss rate across millions of engines, and the result is not a handful of bad ones. It is a recall. Modern engine plants do not treat cleanliness as a vague aspiration. They measure it. Finished parts are washed and then checked against cleanliness limits that cap how much residual debris a component may carry, often expressed as a weight of contamination per part or a count of particles above a certain size. The trouble is that the oil galleries are not simple tubes. They are deep cross-drilled passages that meet at sharp internal corners, and a shaving can shelter in one of those corners through a wash cycle that looks by every external measure like a pass. clean the outside of a crankshaft perfectly, and a single particle can still be waiting in a gallery the spray never fully reached. When GM traced the L87 failures to their source, the trail led to the machining of the crankshafts and connecting rods during specific build windows running from 2021 into the middle of 2024. Microscopic debris had survived the cleaning process and settled into the oil galleries, the internal arteries that feed pressurized oil to the bearings. The first time each engine fired, the debris began to circulate. It scored the bearings and scratched the journals. A rod bearing seized, the rod snapped under load, and the block split open from the inside. That last step is more violent than the phrase engine failure suggests. A connecting rod is a club of forged steel swinging thousands of times a minute. And when its bearing seizes, the rod stops while the crankshaft does not. The rod snaps and flails inside a sealed engine spinning at thousands of revolutions. Mechanics call it grenading. The forensics were what closed the case. When engineers cut open the dead engines, they did not find a cracked design or a part that pointed back to the drawing board. They found scoring, the spiral scratches only a hard particle dragged through an oil film can leave. They pulled oil samples, put them under a microscope, and found fine metallic grit matching the alloy of the engine's own parts. The engine had been sanding itself to death with shavings of its own steel. From there, it was detective work, backtracking through assembly records to find which machining lines, which shifts, and which cleaning stages had let debris slip through, narrowing the suspect window month by month until a handful of build dates stood out. The strangest part is that GM was not alone. Toyota hit an almost identical wall with its V35A twin-turbo V6, the same machining debris and the same contamination of the main bearings, building across the 2022 through 2024 model years. Toyota recalled the Tundra, the Lexus LX, and the Lexus GX over it. And as failures kept surfacing, the company widened the action again and again until well over 250,000 vehicles, roughly 270,000, were swept into the same story. Same root cause, different badge. These are fierce competitors with different suppliers and different plants on different continents, guarding their engineering from each other. And they broke the same way at roughly the same time. That is not coincidence. It is what happens when every automaker chases the same prize under the same rules, and the rules quietly demand more precision than the factories can reliably deliver clean. The shared pressure has a name. For 2 decades, tightening fuel economy and emission standards have pushed every automaker in the same direction at once. Smaller displacement, forced induction, thinner oil, and tighter internal clearances, all in pursuit of a few more miles per gallon. None of those moves is reckless on its own, and each was validated and signed off as sound. But stacked together and pushed to the edge across an entire industry, they narrowed the same margin in the same way, so that when the factories occasionally fell short of perfect, they fell short into the same failure.